Hey guys, welcome to video number 20. We're going to shift gears again and do a little bit of review of complex numbers and coordinate conversions. Complex number, normally represented with the letter Z, can be thought of as a point somewhere on the complex plane. The x-axis is the real axis, the y-axis is the imaginary axis, and we're going to use J to represent the imaginary unit. Mathematicians use I, but since electrical engineers use I to represent current, we're going to go with J. All right, now by definition, J is equal to the square root of -1. All right, J has some pretty interesting properties compared to regular real numbers, and that's what we're going to look at next. All right, to do that, let's just imagine that we drew a circle around the origin with a radius of 1. Okay, I have that over here. It's called the unit circle. All right, let's look at this first characteristic. Raising J to a positive power rotates counterclockwise. I know that's not a rigorous definition, but here's the idea. Whenever you raise J to some positive power, it moves you around counterclockwise. To wrap our heads around this, let's start with J to the 0 power. All right, any number raised to the 0 power equals 1. So here's J to the 0 power, 1. All right, J to the first power we know is simply J. Right, and that's right here. And we know that J squared equals -1. That's from the fundamental definition we have over here. So I think you can see the pattern. J to the 0, J to the first, J squared, J to the third, and so on. So every time we increase the exponent by 1, we rotate by 90 degrees counterclockwise. All right. Similarly, if we raise J to a negative power, we rotate clockwise. So again, starting with J to the 0 power, which equals 1, J to the negative first power would be -J. All right. Now, think about this for a second. Any number to the negative first power is its reciprocal, right? So J to the -1 equals 1 over J. So what we see here is that 1 over J equals -J, and since that's kind of a unique thing, I wrote it here as its own separate pretty equation because that's a handy thing to keep in mind for later use. 1 over J equals -J. All right, J to the -2 would be -1, J to the -3 is J, and so on. All right. Now, we can also raise J to fractional powers. For example, J to the 1/2 power, same thing as the square root of J. What would that be? Well, if J to the first power rotates us by 90 degrees counterclockwise, this would rotate us halfway. It would take us to 45 degrees with a length of 1. Okay? And using this characteristic, we can find any real number of rotation on this circle by raising J to the appropriate power, either positive or negative. Okay, now as far as representations for complex numbers, normally the easiest one to start with is rectangular form. That is, we have a real part and an imaginary part multiplied by J. So that just locates the point by x and y coordinates. This point is 2 over on the real axis, 2 up on the imaginary axis. So z would be 2 plus 2 times j. All right, that's the rectangular representation for this complex number z. All right, now there is another form called the exponential form, and it says that z is equal to r times e to the j times phi. All right, it's a complex exponential, and it's kind of scary looking and hard to wrap your head around. So what we normally do is just use a shorthand notation, the polar notation, where z is equal to m, which is the magnitude r, and the angle phi, and we just ignore the exponential part. We know it's really there, but this is a shorthand that we'll use to represent it. It's a little easier to write and more convenient to work with most of the time. All right, now if we've got these different forms, we can convert between them using these formulas, okay? R is equal to the square root of a squared plus b squared. That's the Pythagorean theorem. Comes from right triangle trigonometry, okay? And the angle phi with respect to the positive real axis is the arctangent of b over a, the imaginary part over the real part. All right, if you're converting from polar to rectangular, that is, you know m and phi, you want to know a and b. A equals m cosine phi, b equals m times the sine of phi. Okay, now that's a lot of stuff to absorb in a short time, so let's make it a little more concrete by doing some problems. All right, we'll start with rectangular to polar conversion. Our first number, z1, is equal to 4 plus 3 times j. 4 over in the real direction, 3 up in the imaginary direction. We want to know what r and phi are for this complex number. All right, r is equal to a squared plus b squared. Take the root. So we got 4 squared plus 3 squared root. That's the square root of 25, which is 5. So this vector has a length of 5. All right, the angle phi is equal to the arctangent of the imaginary part over the real part. Arctangent of 3 over 4 is 37 degrees. All right, so we could say that z1 is equal to 5 at an angle of 37 degrees. All right, next problem. Z2 is equal to negative 2 plus 2 times j. So it's negative 2 in the real direction, positive 2 in the imaginary direction. All right, the length of this vector is just negative 2 squared plus 2 squared root. So that's 4 plus 4 is 8. The square root of 8, which is 2.83 approximately. All right, now when we take the arctangent of the imaginary part over the real part, we get the arctangent of 2 divided by negative 2, which is the arctangent of negative 1. That gives us negative 45 degrees. All right, I'm calling that angle theta, all right, and it tells us the angle up from the negative real axis, but what we're looking for is the angle from the positive real axis, phi. So in order to get phi, we have to add theta to 180 degrees. And so we've got 180 plus theta equals 180 minus 45 is 135 degrees. So Z2 is equal to 2.83 at an angle of 135 degrees. Okay, so first quadrant, no problem with the tangent, arctangent. Second quadrant, we have to compensate by adding 180 degrees to theta. All right, let's do a couple more. All right, the next number, Z3, is equal to negative 5 minus 4 times j. Negative 5 in the real direction, negative 4 in the imaginary direction. So the length of r is square root of 5 squared plus 4 squared, which is square root of 41, 6.4 approximately. Now when we take the arctangent of the imaginary over the real, we have negative 4 over negative 5, which is 0.8 positive. The arctangent of 0.8 is 39 degrees. All right, now what this is telling us is how far off of the negative x-axis we are, which is 39 degrees counterclockwise. Okay, so in order to find the actual angle phi, again we have to add theta to 180 degrees, which gives us 219. So Z3 is 6.4 at an angle of 219 degrees. All right. Here we see first quadrant, no problem with the arctangent. Second and third quadrants, we have to use this compensating factor to actually get the angle phi. What about the fourth quadrant? Z4 is 6 in the real direction, negative 4 in the imaginary direction, 6 minus 4j. All right, the length of this vector is 6 squared plus 4 squared. Take the root. Root of 52 is 7.2. That's the length of this vector. Phi is equal to the imaginary part, negative 4, over the real part, 6. So we've got the arctangent of negative 0.67, which is negative 33.8 degrees, and that is actually the correct angle. Now, we'd rather work with this small negative angle than this really big positive angle. It's easier to visualize. So first quadrant, fourth quadrant, the arctangent is perfectly acceptable. Second and third, we've got to do a little bit of extra screwing around. But anyway, what we get here is Z4 is equal to 7.2 at an angle of negative 33.8 degrees. Okay, let's do some conversions the other direction, polar to rectangular. All right, the first one we've got here, Z5 is 5.66 at an angle of 45 degrees. So we want to know A and B. Well, we know A is equal to M times the cosine of phi. So that's 5.66 cosine 45 degrees. And I know that one off the top of my head. Cosine of 45 is 0.707. So it's 5.66 times 0.707. And I'm going to pull up Windows Calculator here to do this. 5.66 times 0.707 is 4, approximately. So this is about equal to 4, and B is equal to M times the sine of phi. So that's 5.66 times the sine of 45 degrees. And again, that's another one I know. The sine of 45 is the same as the cosine. It's 0.707. So we've got 5.66 times 0.707, which is again 4. So Z5 is 4 plus 4j. All right. If I were to plot that over here, 4 plus 4j is right here. So that's Z5. All right, let's do the next one. Oops. Okay. We've got Z6 equals 4.47 at 117 degrees. So A equals 4.47 times the cosine of 117 degrees. All right, let's find out what the cosine of 117 degrees is. So 117, trigonometry, cosine, negative 0.453. All right, so I'm going to multiply that times 4.47 times 4.47, and we've got A equals negative, let's just call that negative 2. All right, B is equal to 4.47 times the sine of 117 degrees. All right, let's do that one. All right, so 117, and we take the sine. We've got 0.89 times 4.47 is 3.98. Let's call that 4. Okay, so this is approximately equal to 4. So Z6 is negative 2 plus 4j. All right, I'll put that point over here. Negative 2 plus 4j. There's our second complex number. All right, let's do the third one. Let me clear the board. And we've got, let's see, A equals 7.07 times the cosine of 225 degrees. All right, let's pull up our calculator. All right, 225 degrees. Let's take the cosine. It's negative 0.707 times 7.07, and we get negative 4.999. Let's call it negative 5. All right, B is equal to 7.07 times the sine of 225 degrees. Pulling up our trusty Microsoft calculator, we've got the sine of 225 is negative 0.707 times 7.07 is negative 4.99. Let's call that negative 5 again. So 7.07 at 225 degrees is negative 5 minus 5j. All right, so let's see, negative 5 minus 5. Here's our next complex number. Okay, it's on that point. Okay, next, we're almost there. I can see the light at the end of the tunnel. Okay, so let's clear the boards. And we've got Z8A is equal to 5.1 times the cosine of negative 60 degrees. Pulling up our calculator, 60 cosine is 0.5 times 5.1 is 2.55 approximately. And then B is equal to 5.1 times the sine of negative 60 degrees. And let's see what we've got for this. Okay, 60 degrees. Open the trig, take the sine. We've got 0.866 times 5.1. And we end up with 4.4, let's call it. So Z8 is approximately equal to 2.55, and that was minus, I believe. Let me double check that. I'm getting minus 6. I forgot to enter the minus sign for that, didn't I? 60 negative. Let's try the cosine. I think we're good. 0.5, okay, and 60 negative, we take the sine. We got negative 0.866. Okay, that makes sense. I forgot to put the negative sign, but it does give us negative 4.4. So we've got 2.55 minus 4.4 times j. All right, so 2.5 and negative 4.4. That point would be about here. So here are our 4 points representing these complex numbers. And we're closing in on the end of the video. There's just a few more things I wanted to mention. Okay. Why do we bother converting from one form to the next? Well, addition and subtraction are easier in rectangular form. So for example, if we have 4 plus 3 times j plus 2 negative 2 times 2 times j, we just add the real parts. 4 plus negative 2 is 2, and 3 plus 2 is 5. So we just add like parts to get the resulting sum. Okay, and similarly with subtraction, if we had this complex number minus this one, we have negative 5 minus 6, which is negative 11, and negative 4 minus negative 3, which is minus 1 times j. So this difference of these two is negative 11 minus j. Similarly, with multiplication and division, that's easier to do in polar form. 2 at 45 degrees times 5 at 20 is 2 times 5 at an angle of 45 plus 20. So you multiply the magnitudes and you add the angles. 45 plus 20 is 65. The reason we're doing that is because fundamentally these are exponentials, and when you multiply two exponentials, you add the exponents, so the angles add. Right? Likewise for division, 12 at an angle of 30 divided by 3 at 45 would be 12 over 3, which is 4, at an angle of 30 minus 45, which is negative 15. Okay, so addition and subtraction, rectangular form, multiplication and division, polar form. And lastly, how did all this stuff get invented? Well, it was a guy named Leonard Euler, and all of the preceding stuff I've done was fundamentally derived from Euler's formula that says e to the I times phi equals the cosine of phi plus I times the sine of phi. Okay, this is the foundation for all of the complex arithmetic that we do. And there's another form that's called Euler's identity, and that ties together a lot of cool transcendental numbers and fundamental integers. E to the I times pi minus 1 equals 0. That follows directly from Euler's formula. But here's Euler, Leonard Euler, kind of a crazy looking guy, but a genius, and thanks to him we can do all of this kind of stuff. All right, that's it for today's video. We'll continue the next time, probably with a discussion of capacitive and inductive reactance. Okay, see you then.